Okay, thanks for the invitation to the workshop. I'll talk about sub-polynomial cost two-server PIR. This is joint work with my advisor, Rutgers. You can see there. Okay, so let me start with defining what is PIR. PIR stands for Private Information Retrieval. So let me define it formally. Imagine there is a server which has a database A. So let's model the database as just a sequence of n bits, A1 to AN. And there's a user who wants to know the ith bit, AI. So he interacts with the server, and after in general, this interaction can be randomized. The protocol can be randomized. So he interacts with the server, and at the end of the protocol, his goal is to know the bit that he wants AI. But the user is particularly sensitive, and he wants some privacy. What do we mean by that? We want that the user, at the end of the protocol, the user should learn AI, but the server should not learn anything about I, the index that he wants, is looking for. Or more formally, we want information theoretic privacy, which means the distribution of the interaction, the distribution of the transcript is a random variable which is independent of I, the query that the user makes. Right? And this is like the strongest form of privacy, because even a computationally unbounded server, what it sees is a random variable independent of the query that the user is making. So even a computationally unbounded server does not get any information. There is a parallel line of work where you only need to protect yourself from computationally bounded servers. So it's called cryptographic PIR. But in this talk, I will stick to information theoretic privacy. Okay, so the goal is, of course, naturally to minimize the communication cost of the protocol, like how many bits are transferred between the user and the server. And there is, of course, a trivial solution where the server basically sends the entire data, just all the bits of the database. The cost is n, and it's perfectly private because the user doesn't reveal any information about his index. And in fact, this is optimal, unfortunately. Also, I don't understand why that thing changed. I think I originally made it in a Mac, and somehow we changed it to Windows, and it changed it into a really bad picture. Okay. So to solve this problem, Shork, Goldreich, Kushlewitz, and Sudan in '95 introduced the notion of PIR with multiple servers. So now we have and it's assumed that these servers don't communicate with each other, because if they communicate, it's the same as having a single server. So now let's say we have two servers which both have the same database A, and the goal is the same as before. So the goal is the user wants to retrieve a bit privately. So basically, let's say the user is interested in finding the ith bit. So he first generates some random string R, randomness, and he'll send a query to each server. This query depends on the index and the randomness, and he gets back answer from their servers. So the answers depend on the database and the query which they receive. And at the end of the protocol, the user should be able to reconstruct the bit that he wants, AI, as a function of the server's answers and the index and the random string that he generated. So what about privacy? So privacy here means that the marginal distribution of each query is independent of I. So note that the joint distribution of the random variables Q1 and Q2 will depend on I in general. But if you look at the marginals, the marginals are what the servers see individually. The marginals are independent of I. So each server sees something which is independent of I, but the joint distribution can depend on I. Of course, now, the communication cost is again the total number of bits exchanged. So that's the problem. That's the definition of two-server PIR. So this definition can also be generalized to multiple servers and multiple rounds. But throughout this talk, I'll again stick to two servers and just one round protocols. So what do we know about this PIR scheme? So in the original paper where they proposed the CKGS, they gave a two-server protocol with qubit of n cost. So this is already a substantial saving from the trivial n cost, and the dependence on, and if you have more servers, then the cost is like n to the 1 over k. And the dependence on k was improved in further papers. And finally, in a breakthrough, Yakunin and Fermenko constructed a three-server protocol with n to the little 1 cost. The exact dependence is n to the square root log n or log n. So this beats all the previous protocols for any constant k. So this is what I mean by sub-polynomial, n to the little o1. And it was open. Okay, there are some things which broke. So it was open if we can beat the cube root of n with just 2 servers. And we solved this question in this work where we showed that, in fact, you can match the bound of Yakin and Efremenko with just 2 servers. You get exactly the same communication cost. The constants might differ. So that's the main result. So what do you know about lower bounds for this problem? Like what's the minimum communication that you need to do at least for this? So log n is a trivial lower bound. Even if you don't want privacy, just to mention the index that you want, you need to send log n bits. And the best lower bound we know is just 5 log n. And this is by Werner and Wolf. So this is a great open problem, like to improve the lower bound situation here. There is a restricted, a better lower bound of cube root of n for a restricted model of protocols called bilinear group based by Rutgers and Yakinen. And in fact, it captured all the previous known constructions. So if you want to break the cube root of n, you have to come out of this model. And in fact, our work is not captured by this model, otherwise it would be wrong. Okay, so I want to also mention that 2-server PIR protocols are intimately the internal ideas are very similar. That's why I'll explain. Yeah, I mean not in a black box way, but like the objects which they use to construct them, we use the same objects. That's why. So if you improve the objects, then you get the thing. I'll explain what those objects are in a moment. Okay, so I also want to mention that there is an intimate connection between 2-query locally decodable codes and 2-server PIR protocols. So for those who don't know, basically locally decodable codes are kind of error correcting codes where you encode your n bits into using an error correcting code, and the encoding gets corrupted. In a usual error correcting code, you have to read the entire encoding, corrupted encoding, to get back the original message. But if you just want 1 bit of the message, then these codes allow you to decode by just looking at 2 locations of the corrupted encoding. So they allow super fast decoding if you're just interested in 1 bit of the message. So, but there is a lower bound for this. Karindis and Devil showed that if you want to encode n message bits, then 2-query locally decodable codes over constant size alphabet need exponential length. So, and in fact, this is tight. The Hadamard code actually does this. So if you restrict to constant size alphabet, this is the best you can do. And what our result implies is that if you can expand the size of the alphabet, then you can do much better. What you get is there is sub-exponential length 2-query LDCs when the alphabet size is also sub-exponential in size. Okay, so now I'll try to describe what our new scheme. So there are 2 ingredients in our scheme, or 2 ideas which we combine to get our scheme. So one idea is this 2-server cube root of n cost protocol by Woodruff and Yakinen. And the way it works is the servers encode the database using read-Muller codes, which are basically evaluations of a low-degree polynomial. But along with the evaluation of the polynomial, you also evaluate the derivatives, or like the gradient. And the retrieval works by, like, the user retrieves the bit type 1 using polynomial interpolation, but with derivatives. And the 3-server n to the little o1 cost protocol of Yakin and Efremenko works by encoding the database using these codes called matching vector codes. I'll try to describe what these things are. And the retrieval works by polynomial interpolation. So in a very high level, what we do is basically combine these 2 ideas, and we encode the database using matching vector codes, but we also include derivatives. You can think of this matching vector codes as some kind of polynomial codes, and you also add derivatives to them. And the retrieval works by polynomial interpolation using derivatives also. So a bit of notation. I'll use bold letters like U, V, X, Z to denote vectors, and FQ is the finite field of size Q, and ZM, which is Z mod MZ, is the ring of integers modulo M. Okay. So the core, the heart of the constructions is this combinatorial notion called a matching vector family. So to answer this question, if you improve these constructions here, then you improve all the current constructions. So what's this matching vector family? Basically, two collections of vectors u1 to un and v1 to vn, where each vector is k-dimensional with entries in z mod mz. Okay, and the property we want of them is that whenever you take the inner product of two matching vectors, which is if you take the inner product of ui and vi, then the inner product is 0 modulo m. But whenever you take the inner product of two non-matching vectors, ui and vj, where I is not equal to j, then you get something non-zero modulo m. So such a thing is called a matching vector family. Any questions? Okay. So so the way we use these things is that we'll use the left part of the vectors u1 to un. The servers use them for the encoding the database, and the user uses the right part v1 to vn for the decoding. So what do we know about these families? Grolmusch in 1999 constructed, showed that there is a matching vector family or z6 to the k of size n when the dimension k is only n to the little 1. Right? So you can have lots of vectors even when the dimension is like as small as n to the little 1. And there is an important reason why it's z6. It's important that this m is not a prime power. If it is a prime power, then there is a lower bound showing that you need k, the dimension k, to be at least polynomial in n to the omega of 1. So it is essential that this 6, or you can replace it with any non-prime power, but it cannot be a prime or a prime power. So you cannot work over finite fields or stuff like that. You have to go through this composite rings or non-prime power rings. Okay, and moreover, this construction is efficient. It's like an explicit construction, not like an existential. Okay, so how do we construct this protocol? So we start with this matching vector family promised by Grolmusch. So it's of size n, and the dimension k is n to the little 1. And we will work over the ring R, which is formed by adjoining an element gamma of order 6 to the ring Z6. Okay, so these are just polynomials in gamma with coefficients Z6, but gamma has order 6. Okay, so gamma to the 6 is 1. So this is my ring R. So all the things I define will be like polynomials will be over this ring R. Okay, so so given the database A1 to AN, the servers encode it as the following function f. This f maps Z6 to the k to R, to the ring R, and it's defined as follows. F of z is summation ai gamma raised to the inner product of z and ui, where recall that the vectors u1 to un are from the matching vector family. Okay, so to each bit ai, you correspond the monomial next to it is gamma raised to z inner product ui. And also note that the inner product of z and ui is actually living in z mod 6, right? Z mod 6z. That's why we took this element gamma to have order 6, so that this function is actually well defined. Okay, so how does the retrieval step work? So let's say the user is interested in finding the bit a tau. Also, recall that f of z is defined in the following way: it's summation ai gamma gamma raised to inner product of z and ui. To find a tau, the user passes a line through a random point z and z6 to the k in the direction of b tau, where b tau are the corresponding right vector, right matching vector. So he samples a random point inside z6 to the k and passes a line in direction of b tau to find a tau. So if you look at the restriction of f to this line, let's call it g of t. So a generic point on this looks like z plus t times v tau. So if you look at the restriction of f to this line, g of t is f of z plus t v tau is just the summation. I'm just substituting this thing. Is that? Now you can use the linearity of inner product to split the exponent. Now what I'll do is I'll collect all the terms which have the same value of ui inner product v tau. Let's call it L. And I collect all the terms together. So now I have a summation over L in Z6, the sum of all terms which have the same value, L of the inner product of ui and v tau is L, times the gamma to the TL comes out because it's the same in each one. So, and let's call this coefficient CL. So now we have 6 coefficients C0 to C5. And we have this, so the function g of t looks like a linear combination of these 6 coefficients. Okay, so now we use the crucial defining property of the matching vector family. If you look at C0, what is C0? C0 is a summation or all I such that ui inner product b tau is 0. But the defining property of matching vector family is that there's only exactly one vector which gives inner product 0 with b tau, and that is u tau, right? So if you look at the C0 term, it exactly has one term in the summation. And so therefore C0 is a tau times gamma raised to inner product of u tau and z. That's the property of the matching vector family. So the matching vector family allows us to isolate the coefficient a tau that we are interested in from all the rest. Okay, so it's enough to find this coefficient C0 to find a tau. So we have 6 unknown coefficients and interested in one of them. So a natural idea is to form 6 equations in these 6 coefficients and try to solve them to get C0. So how do we get? So the value of f at a point on the line will give you one equation, right? So the main idea is the same as the idea of interpolation using derivatives. So you can interpolate a degree 5 univariate polynomial if you know the values of the polynomial, its derivative and its second derivative at 2 distinct points, because that gives you 6 equations in its coefficients, which are 6 in number. So you can solve them to interpolate the polynomial. So in a similar way, you can if you to get more equations, if you are able to find the value of g prime and g double prime. So here I'm hiding a lot of details because these are not actually polynomials, but there is a way to define derivatives for these functions so that all this makes sense. So if you're able to find g prime and g double prime, then you can get you get 3 equations. If you know g prime and g double prime at a point, even if you know these things at 2 points, then you get 6 equations. And to get g prime, so the value of g at a point is just the value of f at that point. But to find the value of g prime, you need the gradient of f, and you have to take the inner product of the gradient with the direction beta. And similarly, if you know the Hessian, which is the matrix of all second order partial derivatives, then you can find the second derivative of g, the restriction, by chain rule. Okay, so that's the main idea. So this is how the protocol looks like. So as I said, to find index a tau, the user picks a uniformly random point z inside z6 to the k and passes a line in the direction beta. And now he selects 2 points on this line, sends 1 point to each server. So and the servers reply back with the values of f, the gradient of f at that point, and the Hessian of f at that point. And from these 3 values, so from the values of f prime and f double prime, you can use chain rule to find the value of g prime and g double prime at the points t1 and t2 over the ring R. And he gets 6 equations in the 6 unknowns, and he solves them to find C0, and then from C0 you get a tau. Okay, so that's the protocol. And what about privacy? Privacy is guaranteed because if you look at what each server sees. So server 1 sees z plus t1 v tau, but since z is uniformly distributed over z6 to the k, what the server 1 sees is a random point from the space. It doesn't get any information about the index tau. So the privacy is guaranteed. And if you look at the communication cost, so the user is sending a vector of k dimensions, k-dimensional vector to each server, and the server reply back with the value of f, which is just one entry, f prime, which is the gradient, has k entries, the set of all first order partial derivatives, and f double prime, which is a matrix, k by k matrix of all second order partial derivatives, is the largest term, so it has k squared entries. So the total communication is order k squared, but k is still n to the little of 1, so the communication cost is still n to the little of 1. Okay, so that's it. That's the protocol at a high level. There are some issues where, because these are not really polynomials, and these are not polynomials or finite fields, the problem of interpolation or these kind of rings, but these are all technical, and at a high level, this is the idea. Okay, some open problems. So we really don't understand these matching vector families. So we want to know how large should k be to get a matching vector family of size n in zk to the n, zm to the k. And the current upper bounds by Baumeick, Dwyer, and Lovett do not even rule out log n, log n communication using our approach. So we really don't understand. Maybe there are such good matching vector families that we get like polylog communication just by using this method. Or independently, you can try to improve lower bounds for two-server PIR schemes. As I said, phi log n is the best we know right now, and it's a really great problem to improve this lower bounds. And the lower bounds, as I said, is also related to lower bounds for two-query LDCs or a large alphabet, which also is very mysterious. We don't really understand them. And in fact, there is a really nice connection, as recently shown by Andoni et al., that if you get better lower bounds for two-query LDCs or a large alphabet, you can show tight time space trade-offs for approximate nearest neighbor search with two-cell probes. So this lower bound problem has also implications for lower bounds in other interesting algorithmic applications.
So they show that if you have better, what direction did they show?
So they showed this direction, exactly. So they showed that if you can prove lower bounds for two-query LDCs over a large alphabet, then you can get time space trade-offs for approximate nearest neighbor search with two-cell probes where the cells are large. So the current bound they get is limited to what we can show for lower bounds for two-query LDCs. The current lower bounds only work when the alphabet size is really, really tiny. As long as it goes slightly large, the lower bounds completely don't work. So they are limited by this problem. I see. All right. So in fact, even our result shows that you cannot get like exponential or any good lower bounds or like sub-exponential. I mean, our result shows that there are in fact sub-exponential LDCs when the alphabet size is sub-exponential. So the exact trade-off is trouble. Another nice interesting question is, does interaction help? So all the current upper bounds we have are just single round, in the sense that the user sends something and the server reply back. But we don't really know if interaction helps. There is no reduction saying that if you can convert an interactive protocol into single round or like any interesting applications of interaction. So that's another interesting open problem. So I'll end with that. Thank you.
You try to figure out the break-even point between your protocol and the cubic protocol that has a small multiplicative function. Like, so what is the minimum value of n?
I haven't actually worked out the constants, but I think for any reasonable n, the cube root of n would be better.
Okay, thanks again.
Thank you.